Okay. Today, two topics. Number one. Derivative formula. Not from Taylor expansion, but from polynomial interpolation. Differentiation via polynomial interpolation. Okay, now second 7.2 numerical integration. Integration. How to accurately compute an integral. Okay, compute integral. Now topic one. Given a table. Connect data. Okay. Connect data. Y0, Y1, Y2, and Yn. The polynomial that interprets this table is, say, there are several forms. Here I use a Lagrange form. Okay, the polynomial that interprets this table is this summation 0 to n. Function value at xi. Yeah, xi is yi, and then cardinal polynomial li. Yeah, li. How close is interpolation polynomial to the function m? Yeah, the formula is here. Yeah, how close? Yeah, so close. Error term is 1 over n plus 1. Yeah, and then n plus 1 derivative on f. Then evaluate at some point. This point, of course, depends on x. And then times this. Okay, product I from 0 to n, x minus xi. Yeah. Okay. Now interpolation polynomial. Yeah. When collecting data is expensive. Yeah, just like this case. Yeah. So we only have a table. And x0, x1, x2, xn are fixed. If collecting data is not expensive, you can use the formula in the last several lectures. They use this formula. F roughly derivative is x plus yeah, and then minus h, then over h. Yeah, you can choose any h yourself. Say choose one. Okay. Then suppose x some number, say square of 2, say for example. Then choose 1, then square of 2 plus 1. Okay. Now go to do experiment to collect the data. Then if you think h is too large, then choose say 0.1, then collect data again. Suppose collecting data not expensive. Okay? You don't need to spend much money. Okay? But when data are expensive, yeah, we only have this data. Okay, so how to do computation? How to compute derivative? Right, now take derivative on this equation. Let me see. Eraser. Yeah. Take derivative. Yeah. Derivative. Take derivative. Then P derivative. And then error. Error. Okay. Take derivative. Now compare. Okay. Derivative on P. Okay. F of xi. A number. Data. Number. So take derivative on P. Actually, take derivative on Li x. So this is a summation I 0 n f x I then Li derivative. Right, now take derivative. Let me see. Take derivative on this. On the error. Yeah. This is a product of this function. Yeah. This depends on x. When something depends on x, it is a function. Yeah. Psi depends on x. So this is a function. Times this function. So other formula. So n plus 1 factorial. Now take derivative on n plus 1 psi x. Then times take derivative on this other formula. And then plus then derivative. Wait. Hey, for x, a general x, we cannot simplify this form this equation. How about let's consider derivative x sum lot. Okay, say yeah. If x is xk, okay, xk is a lot, then this equation can be simplified. Derivative at xk is summation I from 0 to n f xi times li xk then plus x minus xi I from 0 to n. So when I plug in xk, this is 0. Okay. So this term is gone. Okay, gone. So plus n plus 1 sine x times derivative 0 to n. This is a product. Take derivative. We also have a formula. Say, f g h derivative is equal to the formula f derivative times g times h plus f times g derivative times h. Then f g derivative on H. Yeah. Yeah, same, okay. A product x minus x0 times x minus 1. Okay. Take derivative on each factor, make a sum. Okay. Then plug in xk. Plug in xk. So this is plug in xk. So we get so this is okay. Yeah. Take derivative, okay, then plug in xk. Then this is a summation I from 0 to n f xi li sk then plus n plus 1. Sign depends on x. Now plug in sk in x, so xk, yeah. Then compute derivative, then plug in sk, then that is j from 0, j log equal to 0 to n xk minus xi. That is the formula to compute derivative at one look. Yeah, yeah, you can use interpolation polynomial. Yeah, let me show you one special case. Okay, the data table has data x0, x1 to xn. Now let me consider n is 2. Okay, special case. Consider n is 2. N is 2. Say special case. Okay, the n is 2. Then the table is x0, x1, x2, y0, y1, y2. In this special case, L cardinal function L0 is L0 is 1 at x0 and x1 at x1, x2. L0 is 0. Then it is x minus x1 times x minus x2. Then over this guy, when x is x0, the value is 1. So plug in x0, plug in x0. Yeah, it is x0 minus x1. X0 minus x2. Yeah, yeah. So yeah, this function, when x is x0, value is 1. When x is x1, value is 0. x2, value is 0. And L1 is x minus x0, skip x1 minus 2, then plug in x1. X1. L2. L2 is x minus x2, x minus x1, then x2 minus x0, x2 minus x. Now, I want to compare. Suppose, okay, suppose we find derivative of the function at one looked, say at x1, okay, at x1, say suppose. Right. Now, here, take derivative, right? Then compare derivative on L. not difficult because this is a polynomial of degree 2, take derivative. So it's not difficult. So we get together with error term. Yeah. Derivative at x1 is equal to, together with error term is equal to what? Function value at x0. This is y0. Y0. Then times x1 minus x2. x0 minus x1. x0 minus x2. Take derivative on L. Then plug in x1. Okay, then plus function value at x1 to x1 minus x0 minus x2. Then x1 minus x0, x1 minus x2. And then plus f x2. This is from the Lagrange interpolation polynomial. Take derivative, then plug in x1. Error term, error, 1/3 factorial. Sign depends on x1. Then x1 minus x0, x1 minus x2. To get a formula, okay? Any 3 points, x0, x1, x2. I want to compute derivative at x1 formula. Let's consider a special case. Okay. Consider a special case. Special case. X0, x1, x2 are equally spaced. X1, x2, x0 equally spaced. That means that the distance, equally spaced. Distance between x0, x1, h, between x1, x2, h, equal space. Consider this. That's the case. Now, this formula can be simplified. Can be simplified. Can be simplified, okay? Then f x1 derivative is equal to f x0, negative h, x1 minus x2, negative h over x0 minus x1, negative h, and then x0, x2, negative 2h. So the bottom is a 2h squared. And then plus second term, f x1 times, simplify. X1 is x0 plus h. So here, simplify, okay? Then 1/2h. No, this term is 0. Why it is 0? Let me compute this in detail. 2x1 minus x0. So this is x0 plus h, right? minus, yeah, minus, okay. How about this? This is a x0 plus 2h. Yeah, I think so. Cancel out x0. 2h minus 2h, yeah, exactly 0. So yeah, this term is 0. I suppose the 3 points, they are equally spaced. So yeah, this term is 0. How about this term? Okay, this term simplified is plus f x total times 1 over 2h. Yeah. Okay, now error. Error. It is 1 over 3 factorial. Third derivative at some point sine 1. Okay, sine 1. X1 minus x0 h. X1 minus x2 negative h. What is x0? X0 is x1 minus h. X2 is x1 plus h. Okay. Now cancel out this h. F first term, third term. Then we have f x1 plus h minus f x1 minus h, then over 2h. Error term is minus 3 factorial is 6, so 1 over 6. Take derivative 3 times sine x1 h squared. Actually, this formula is the formula in one previous class. This is a order 2 formula to compute derivative at a point. Yeah, order 2. Truncation error is order 2. So there are some connection, okay, about formula from interpolation polynomial and formula from Taylor expansion. Taylor expansion assume all the points are equally spaced, but interpolation polynomial doesn't assume the roots are equally spaced. This is just a special case. Okay? Special case. When equally spaced, formula from polynomial interpolation reduced to formula via Taylor expansion. But this formula can handle a general case. Right? The roots are not equal spaced. That is the difference. Okay, now the second topic, I want to develop formulas to compute an integral. Okay, integral. Yeah. Numerical integral. Numerical integration. I want to compute it. Okay, a to b function n. The idea is find a simple function. Okay, function a g. Okay, simple function g. and use G to approximate function f. And then compute integral on G. Yeah, that is the idea behind. How to choose a simple function? Yeah, now we have several choices. Say I can choose a interpolation polynomial for G. I can choose spline function, say cubic spline for G. There are other choices, okay? There are other choices in the book. But okay, now let me present the choice. I use interpolation polynomial for G. Okay. Yeah. Here, interpolation polynomial. Given a table. Given a table. Given a table, yeah. X free, xn, y free, y. Now, the polynomial that interpolates the table. Now this time, I use Newton form, not Lagrange form. Okay. Okay. Now the polynomial is P f x0. Yeah. Divided difference, then Q0 plus f x0 x1 Q1, and then plus f x0 x1 xn qn. What is Q? Yeah, Q is where Q0 is equal to 1. Q K is x minus x0 x minus x1 x minus xk minus 1. Yeah, in Newton form. In Newton form. Yeah, the error is function f. We always need the error term because we want to know, how good is approximation to the exact value of an integral. Yeah, we need to compute integral on error term. Yeah. Error term is 1 over n plus 1 factorial. Okay. N, okay, n. X minus x. This is an error. Yeah, error term. Yeah, error. Okay, now take integral on the both sides. Okay. Take integral AB, then integral on interpolation polynomial, then integral on error term. Yeah, error term. Integral on error term. Error term. Error term. Yeah, error term. How about use En x to below the error term. Right? Polynomial is this. is this, okay? Apply integral to the polynomial. Then we have summation 0 to n. Yeah. Dividing difference is constant coefficient. So here is a dividing difference x0, x1 to xi. Then integral 0 to a to b, qi x. Yeah. Then plus error. Plus error. Qi polynomial, yeah, this product. So integral computable, right? Easy to compute it. Integral. Take integral on this polynomial. Now drop the error. Drop the error. Okay. Drop the error. Then we have a formula to compute an integral. Yeah, we have a formula. Yeah. The formula. Drop. So formula. Summation I from 0 to n. Xi. Now this is general idea. Now consider some special case. Okay, consider some special case. First case, special case. Okay, this case, the resulting formula is called trapezoid rule. Okay, trapezoid rule. Trapezoid rule. Trapezoid rule corresponds to the case n is 1. Okay, n is 1. N is 1. The case. N is 1. So n is 1, and also set x0 to a, x1 to b. Okay, yeah. In this approximation, set n to 1, x0 to a, x1 to b. Yeah, a, b. Okay. Then, yeah, let's see what we will get. Okay, yeah. Here, I use this equation. In this case, AB dx is equal to, yeah, divided difference at x0. X0 is a, yeah, first term, right? And then integral AB on Q0, yeah, dx. Then in the first step, I still use x0, and then f x0 x1 integral on q1, n is 1, then plus error term. Plus error term. Yeah. Now let me plug in a, b in x0. Here it is. That is f x0 is a, then q0 is 1, x0 is A, x1 is B. Then integral AB. What is Q1? Q1 is x minus x0. So x minus A dx, then plus integral AB E1 x. Right. So right here is this is order 0 divided difference. It is function value at A actually. This guy. Function value at A. Integral from A to B on the function 1 B minus A. Okay. Now, how about this? Divided difference of order 1. We have a formula. It is function value at B minus function value at A, then over B minus A formula. This integral easy to compare. Yeah, this is easy. Anti-derivative, then plug in B, plug in A. Fundamental theorem of calculus. So this is B minus A squared over 2, then plus error term. Right, now I can see that, you see, I can cancel B minus A, right? B minus A, yeah. And then B minus A, factor it out. Then the first two terms is B minus A over 2. Function value at A, function value at B, then plus error term. So drop the error term, drop. Okay. Roughly is this. Okay. The number on the right side of this approximation is area of trapezoid. Yeah, area of the trapezoid. If I let me draw the graph of the function f. Graph of the function f. Yeah. Okay. Graph. Okay. This is A, B. Graph. Okay. Here. Integral is area of this region. Yeah, this region. Integral. This region. This is an integral. The right side. This number turns out to be the area of this trapezoid. Yes. Connect these 2 points. Yeah, the green. Yeah, the green one. The green region, trapezoid, its area actually the right side. Yeah, 1/2 function value at A, function value at B. Function value at A is height, function value at B is height. 1/2 the height and the height, the sum of it, average, then times the length, B minus A. Yeah, this is a trapezoid area. Okay, now an important question is How good this approximation is, you need to compute error. How good? Okay. Now let me compute error. How good? Yeah. Let me compute the error. Error AB E1 x dx is equal to AB 1/2 function second derivative. Yeah, the error formula. Okay. Sine and x minus a, x minus b. Yeah, derivative. Compute it. Please note that the product in this product over the interval AB, this product doesn't change sign. Let me see. When x is in AB, x minus a positive, right? This is positive, right? X minus b, this is negative. So this product everywhere negative on the interval AB. We have a formula in the class at the beginning of the semester. We have a formula. This is called mean value theorem for integral. AB U V take integral. If some function say V doesn't change sign, okay? This is always positive or always negative. Then this integral I can move out U, okay? I can move out U. I can find some point between A and B, say the point sign, such that integral of the product is equal to this. Yeah. Yeah. You can go home and take a review. Okay. Yeah. Hey, now this product doesn't change sign between A and B. Now I can move this up. Okay. I move on. Okay, move on. Actually, this guy sine x depends on x, so this guy depends on x. It is a function, so I can find some point x between A and B. Yeah. So move this up. Let me denote the point just like sine. Okay, sine some point. Okay, some point between A and B. Yeah. Take this A B. This integral is computable. Computable. Yeah. Expand the product, then take integral. Computable. Then what is the result? It turns out that this is a negative 1/12. Second derivative at some point sine, then b minus a. Yeah. How good this approximation? Yeah. Let me add the error term here. Yeah. Add minus 1/12. Then second derivative b minus a. So now after I add the error term, this approximation becomes an equation. Yeah. It's an equation. How good? Depends on the interval. If b minus a small, say less than 1, or much less than 1, then error is small. Say B minus A, 0.1. 0.1 to the 10 to -3, small. Okay. Of course, we assume this guy not to be, okay. But this is the general case in application, okay. Even though we don't know function n, derivative usually smooth, not too big. Okay. But however, on the other case, okay, B minus A greater than 1, say 10, 1, 10 to the error is big. Now, when A, B, this interval is large, how to obtain a good method in the case at the interval, okay? Yeah. But I don't have time, okay? But let's class. We cut the interval AB. Right here. AB. AB. Okay. Say introduce lot. Okay. Say call this T0. Then cut T1, T2, Tm minus 1. Yeah. This is a Tn. Yeah. Cut interval AB so that each subinterval is small. Then apply trapezoid rule to each subinterval. Make a sum. Okay. But this I present is next class. Yeah. So for numerical integral, the key point is handle the error. Okay. Error. Okay. Let's stop here.